So as usual, I'd like to begin by thanking the Cornell Atkinson Center for Sustainability for the support of the seminar series. So it's my great pleasure today to welcome Dr. Filiz Garip to the seminar series. Her career has followed a rather remarkable path. After immigrating to Turkey as an infant with her family and growing up in a small village, she's able to attend Bosphorus University, where she studied industrial engineering as she was good in math. Subsequently, she then moved to Princeton to earn her master's degree in financial engineering. And it was there that she decided to switch fields to earn a PhD in sociology at Princeton. Filiz Garip is now back in Princeton as professor of sociology and public and international affairs. Her research lies at the intersection of migration, economic sociology, inequality. Within this general area, she studies the mechanisms that enable or constrain mobility and lead to greater or lesser degrees of social and economic inequality. She's author of a book on the move, changing mechanisms of Mexico-U.S. migration, and has authored many papers, among them the application of math to sociology through machine learning. So welcome, and look forward to your seminar.
Thank you very much. Thank you for the invitation, and I look forward to the questions as well. I'll be reading them after my talk and trying to answer them. So let me start by sharing my screen. And much of this work actually started when I was still at Cornell. And you'll see, maybe you'll recognize some of the names on my slide, my colleagues at Cornell who are part of this project. And our project was also similar to the seminar series, was supported by the Atkinson Center, their grant, and also a grant from the Migrations Challenge, Grant Challenge that Cornell University instituted recently. So I'm going to talk about how weather events are linked to migration, human migration between Mexico and the United States. And my collaborators include a Cornell economist, Nancy Chow, as well as Amanda Rodewald, who's in the Department of Natural Resources and at the Lab of Ornithology. So she studies bird migration. And we thought similar insights could be applied to human migration as well. And we have two students, or former students, in the case of Mario Molina, who's now a postdoc at NYU Abu Dhabi, and Julia Zhu. So I'm going to be talking about two related papers in this as part of this project. And the first paper is spearheaded by Mario, and the second paper, Julia is actually helping us with that project. So there's growing interest in how human migration can be linked to environmental events. And the context of climate change is obviously a reason for this increased interest. We expect extreme weather events to increase both in severity and frequency in the near future. And naturally, we worry about the human displacement as a result. Now, research to date, or social science research to date, I need to clarify, has focused mainly on gradual changes in weather over time, mostly in changes in temperature and precipitation. And they've looked at how this has impacted human mobility. There's also a separate strand of research looking at more extreme events like hurricanes or natural disasters and how that also affects mobility. But in this kind of part of the research, we're only focusing on gradual changes, and we're looking at it from a historical perspective. Now, we've already started to accumulate some really important findings in this literature. And some of these findings are really intuitive and they're consistent across studies. For example, Kaivan Munshi, who's an economist, was one of the first to establish a linkage between lower rainfall in Mexico and more US-bound migration. And he suggested agricultural yields as the intervening mechanism between weather and migration patterns, and later work measured these yields kind of more precisely, like Feng and others' work at PNAS, and they show that really kind of low rainfall in Mexico lowers the crop yields, and this in turn leads to more US migration. But as we accumulate more and more findings, we see more mixed results, and it's not clear what to make sense of those results. For example, Rios Mena and others have studied again the Mexican setting, and they found that low rainfall is associated with more migration, but this only happens in well-off communities. And their interpretation was, because migration is a costly undertaking, especially undocumented migration, for which you need to hire smugglers in the Mexico-U.S. context, it's only well-resourced communities that would be able to finance those trips. But then when they looked at extreme temperatures, they actually observed the opposite pattern. They found that extremely high temperatures were linked with more U.S. migration, but that only happened in poor communities. And it was harder to explain this pattern. Now, this is just one example, but it's pointing to a larger problem in the literature. We're accumulating a lot of mixed findings because it's very hard for social scientists to know the correct specification for weather fluctuations. In other words, how do we think about weather impacting human decisions? First of all, from just a geographic perspective, each community has a different normal temperature, right? So cold weather in Ithaca doesn't mean the same thing as cold weather in a Californian town. So basically, studies go about correcting for these normals, but they do it in different ways. So some studies argue that we need to look at the long-term normal. So they look at Ithaca's temperatures between, let's say, 1960 and 1990, and then look at the deviation of today's temperature from that normal period. Other studies argue that a 30-year period is too long. We should look at the recent decade. And that obviously changes the results. Second, we don't know how humans respond to these weather changes. Do they respond immediately, or is there a delayed response? And if there is a delay, with what lag does it happen? Do you care about last week's weather or last year's weather, or do you look back to 2 years ago? And then we also don't know how kind of the response happens. Is it cumulative in the sense that you don't observe an effect for a few years, and then suddenly when it accumulates to a certain threshold, suddenly you see an impact? And we would call this intensification. For example, imagine a community has an irrigation system. So 1 year of low rainfall does not really affect them. But if there's consecutive years where there's shortage in rainfall, then suddenly you might see an impact once kind of the irrigation dries out. Or you might kind of expect the opposite pattern. You might observe that weather fluctuations create a decaying response because humans adapt. They change crops, and that way the same weather conditions do not create the same kind of migration response. So basically, we have many different possibilities to think about the linkage between weather and migration flows. And we can say that this kind of association can be characterized by complex interactions between contemporary weather, what's happening now, and what's happened in the past. And we can think of, various lags, not just kind of last year, 2 years ago, but we can take it back. And then we can also imagine that weather would interact with other social and economic factors at the household or community level. We can expect that more vulnerable communities might give a higher response or a lower response, or communities that have an established migration history might resort to that strategy more easily. So basically, the question is, how do we take into account all of these complex interactions between kind of weather across time, and also between weather and other social and economic factors? Now, one potential issue is we might end up with a model, if we consider all of these possibilities, that has more parameters, more things that we would like to estimate than observations. So let's say that you have 50 different indicators, and you want to consider all interactions between them. So if you consider all possibilities, that gives you 2 to the power of 50 possible parameters, and that almost certainly exceeds the observations you will have. And second problem is, even if you were to come up with a sufficiently complex model that doesn't run into these kind of limits, you might still overfit the data if your model is too complex. Now, this means that you would be capturing the noise, the idiosyncrasies of the data at hand, and your model, whatever it is, will not generalize to another data set. So how do we solve these issues? So in the first part of the project, we basically started using a different methodology than is commonly used in the social sciences, which applies machine learning tools. Now, these tools allow us to fit complex models without overfitting the data. Now, machine learning, some of you might be familiar, is a field, a very fast-growing field that sits at the intersection of computer science and statistics, and its goal is to automate discovery from data. So in the past, intelligent systems basically involved coding all possible outputs for all possible inputs. So you basically hard coded these decisions. But nowadays, these automated intelligent systems learn from data by estimating complex functions. And with Mario, we actually wrote a review article for social scientists on this if you're interested. Now, there we talk about two main classes of machine learning. So one class that's called unsupervised machine learning typically discovers representations of some input X. So you might want to, for example, look for groups among migrants based on certain characteristics, which I did in some of my earlier work. But here we're using a second class of methods, which are known as supervised machine learning. And here your goal is to explicitly link an input X to an output Y. And your goal is to be able to make predictions on new, previously unseen data. Now, in the social sciences, this is not how we think about data analysis. Basically, most of us use ordinary least squares or some version of it, where you propose a simple parametric model that could have generated the data. So you're already kind of writing an equation that describes the link between weather and migration. And then you estimate the parameters of that model from the data, and then you interpret those parameters. Now, the downside of this simple approach, which is obviously quite powerful, is it ignores model uncertainty. So we don't consider all possibilities of models. We stick with simple models. We don't consider really complex interactions. And we don't often consider out of sample performance. So basically, we use the same data to estimate our model and to evaluate its performance. Now, in supervised machine learning, you consider complex, often non-parametric models, and your goal is to achieve predictive accuracy. But the downside is you often end up with black box results. In other words, you give the model certain inputs and you can predict the output, but you don't exactly see what the relationship between these two kind of vectors are. So you don't gain insight into the mechanism, producing that relationship. So we kind of took those downsides as given, and we wanted to kind of answer this very simple kind of or basic question that we haven't to date answered. Can we really predict migration at the individual level with the data that we have? And then can we predict it better when we include weather and all sorts of weather measures? Now, the method that we use is based on the so-called regression trees. So here, regression trees involve a tree-like model, and it's describing a sequence of splits in your input space, and you have a prediction for your outcome Y at the end node. And it's good for capturing nonlinearities and interactions in your inputs. So very simple example, let's say we want to predict migration, which is a 0-1 decision, and we have two indicators, age and education. So we can imagine a regression tree first splitting your sample by age. So you're dividing your sample into young and old. And then each branch can further split into two categories by education, college educated and non-college educated. And then at the end of each of these nodes, or at the leaf, you have a prediction. So in this case, we have a prediction of 1 for young college-educated individuals. And you can see that with enough branches in a tree, you can perfectly predict your data. But you don't want to do that because then you would be capturing the noise in the data as well. So you put some kind of constraints around how complex you allow your model to be. So we use a version of these methods that use estimates from like thousands of trees. And this kind of gives, this leads to kind of the method called random forests. So you're not just estimating one tree, but you're growing a forest. And the reason for doing that is you want to kind of increase the predictive accuracy, but this also means that you have less interpretable relationships between X and Y. So you can't just draw the one tree like I had in the previous slide. Now, the setting we're considering is the Mexico-U.S. migration, the largest international migration flow in the world, also the largest sustained movement between any two nations. And the migration between these two countries goes back to kind of 1800s, but it really started to gain steam after the 1960s, after the Bracero program that brought Mexican workers as agricultural laborers to the United States. And then this program, the guest worker program, came to an end at that time in, I think, 1964, and then undocumented migration flows started. So now, today we estimate about 11 million undocumented Mexican-born individuals are in the US. About half of them are undocumented. So really a huge flow, also a flow on which we have a lot of data. So the data come from the Mexican Migration Project. So the project team started in the 1980s. And each year they went to Mexico and they selected 3 or 4 communities. And in each community, they first did an entire canvassing of the community. So they would draw these maps with household names or household numbers. And then they would randomly select 200 households. And then they would interview everyone in those households. And if there was a migrant in that household who was absent in the US, they collected his or her information from those left behind. And they tried to connect with some of these migrants in the United States as well. And they also collected detailed life history information. So for these individuals, we have information on their educational histories, their labor histories, also their first and last migration trips to the United States. So basically, even though the data were collected cross-sectionally, we can basically expand it into a panel format. So right now, the project is still ongoing. To date, it has collected data from 170 communities in Mexico. These communities come from 21 states. So the data are not nationally representative of the Mexican population, but they do provide an accurate representation of migrants to the United States. So researchers have done some comparisons with alternative national data sets, and the data are pretty good in capturing communities where migrants originate from. So we have information from about 140,000 individuals. 20,000 of them have migrated to the US at least once. And we're observing these individuals between 1980 and 2019. Now, we take this social survey and we overlay on those weather information that comes from the NASA Earth Observing System. So we use the gridded data that cover every kilometer square space on Earth and provide, daily measures of precipitation and temperature. And we basically compute aggregate community level measures by averaging over the grids within each community boundary. And these communities are really, really tiny. Now, one of these lessons that we learned very quickly was how important it was to measure weather at a fine-grained scale. A lot of the work in the literature that I cited in the beginning uses state level or at best municipality level information on weather fluctuations. Now, we saw a big difference when we did that and compared our measures to those more aggregate measures. So here I'm showing a map of Mexico, and these states are color-coded with respect to their precipitation that they received in year 2000. Now, we're correcting each state by its own normal. Basically, we're measuring the state's rainfall between 1980 and 84. That's our normal period. And for year 2000, we're looking at how much the rainfall in 2000 deviated from the mean rainfall in the normal period. And we're dividing it by the standard deviation in the normal period as well. So how much you've moved from the mean in terms of the standard deviations. And if nothing has changed, so if a state is receiving the same amount of rain it did in 1980s, we would expect to see kind of a white shading. So red means that states are receiving less than normal, and blue means that they're receiving more than normal. So if we look at the state level map on the left-hand side, we see that most states are either white or shades of pink, which means that they either receive the same amount or slightly less than they did back in the 1980s. But then on the right-hand side, we see the same map with municipality level information, and we see a lot more variation. So if we pick one state of Sonora in the green rectangle, we see that in the state level data, we can discern no change because it's kind of white. But then if we look at the municipalities, we see all these kind of microclimates within that state. Some states receiving a lot more than normal, other states receiving less. So our communities in these data are even smaller than municipalities. So there's even more variation. And actually, our results show that municipality and state level aggregation is just too coarse. It's not really helpful in capturing the changes. And same thing with precipitation. So we spent over 2-3 months just kind of trying to merge these different data sets. And it's really, in the end, it turned out to be really important. So the output that we're focusing on is the first migration trip. We're not focusing on repeat trips because there's path dependence. Once you migrate once, your decision-making process for the second migration might be different. So we want to avoid that kind of endogeneity. And in terms of inputs, we use kind of different combination of these inputs, but we have information on age, sex, education, on household assets, including land, properties, and businesses. We have information on the migration experiences of all household members. And we also know community involvement in agriculture, and we also can compute migration history of that community. So what share of community members have migrated at least once? And there's big variation in our data in this. In some communities, 1 in 10 has migrated. In other communities, 6 out of 10 have migrated in a community. And that makes a difference. So when it's come to weather measures, we basically scan the entire literature on weather fluctuations and migration, and basically computed every measure that we could find. And we included annual lags for each of these measures going back 5 years. So remember, the advantage of these supervised machine learning tools is that they can handle really kind of a lot of data, and we're hoping that they will be able to select the measures that are most predictive of migration patterns, but more on that in a minute. Now, this brings me to an important point. In the typical methods that we apply in the social sciences, like ordinary least squares, our goal is to achieve best in sample fit. So we use the same data to select the model and to assess its performance. And we look at things like R-square, the share of explained variance. In supervised machine learning, the goal is not to predict just well in your sample, but to predict well out of sample as well. So to achieve that, computer scientists typically divide their sample into 3 groups. So we do the same here. We use our training data to fit different models. And then we use validation data and another portion of our data set to select the best model among them. And then there's a test data set that we keep in the vault still to assess the final performance of our best model. So that way we're hoping that we can evaluate, how well our model performs on a data set that it hasn't seen. So the way kind of we do the splitting is we set aside half of our data, half of the individuals in our data into training data, and then the remaining we divide into halves. Half goes in the validation, 25% of the overall data, and the rest goes on the test data. Now, the question is, can we predict migration? If we're kind of really naive about it, yes, and too well, because our data are very imbalanced. So remember, we have, for all of 140,000 individuals, several observations over the years, about 2 million person years in total. So among them, there are only 20,000 first migration events. So this is less than 1% of the observations. So if we build a model that predicts not migrating all the time, it's accurate 99% of the time. So this kind of quickly tells us that we can't look at the average accuracy of our model. We need to look at accuracy within migrants and non-migrants. When we do that, we see that our predictions are not good at all. We actually do okay in the training data. So if we look at the performance of our model in the data set that we use to fit it, we see that we can predict non-migrants with 100% accuracy, and we can predict migrants with 87% accuracy. Not bad. But then if we actually use the validation data, you can see the true performance of our model is really terrible. For non-migrants, we can predict 99% of the time. For migrants, only 6% of the time. So this is telling us that we're overfitting the data. Our model is getting too complex, to kind of learning the features of our training data and capturing the noise, and it's not generalizing well. So we basically need to solve this problem. We put more restrictions on how complex our model can get. So we restrict the tree depth. We also increase the cost of making a mistake for migrants versus non-migrants. So the relative weighting of these errors. And when we do that, we can see the trade-off, right? So if we increase the cost, we can see that our predictions for non-migrants are going down, but our predictions for migrants are going up to about 50%. And again, if we kind of do an extreme weighting, we can predict migrants perfectly, but this time we're really failing with non-migrants. So basically, it's up to the researchers to decide what the best model is, depending on what your goals are. Now, here, up until now, I did not introduce the weather indicators into our model. We were only using individual, household, and community level factors. So can we predict migration better with those weather indicators? Now, to see that, we're going to look at a different figure that is often used to evaluate the performance of different models. And this curve is called the receiving operating characteristic curve, or a ROC curve. So here you're plotting the true positive rate in your model on the y-axis against the false positive rate on the x-axis. So if you had a perfect model, it would just jump to 1 immediately and then stay there no matter what you changed in your model. Now, researchers typically look at the area under the curve here, and a perfect model would have an area under the curve of 1. So the closer your curve to that ideal, the better the fit, the better the accuracy of your model. So here, these curves in different colors are all for different models. The red curve is for the case when we have no weather data. And then the other ones are with alternative combinations of weather information. So the area under the curve for the red model with no weather data is about 0.78. So it has average accuracy of 78%. When we introduce weather into this, our predictions, actually predictive accuracy or area under the curve, moves up to 80 to 81%. So yes, there is an improvement, but it's really, really minor. And then if we ask the question of how does this complex modeling infrastructure perform relative to a simpler model? So to answer that question, we fit a simple logit regression. Logit regression accounts for the fact that our outcome is binary. And we hand selected a few weather indicators in addition to the individual, household, and community level indicators. And the area under the curve of that model was 78%. Not that different from kind of the more complex models. Now, this outcome is actually not that surprising. There was a recent effort to bring more of machine learning tools into social sciences, and a team at Princeton University actually set up a mass collaboration effort. So they made available a social science survey called the Fragile Families Data to the scientific community, and 160 teams basically signed up to this competition. And the goal in the competition was to use the available data to build models to predict individual level outcomes, like your GPA, whether your family gets evicted, so on and so forth. And then each team's models were evaluated on a new test data set. Basically, what they found was, regardless of the method used, the predictions were not good at all. And the teams all, in a way, failed in predicting these individual level outcomes. And they found that, again, a simple model with a few expert chosen indicators performed just as well as the most complex and the best performing machine learning models. Now, I wrote a commentary on that effort that appeared in PNAS. And I think some of the things that I said there actually apply to this setting as well. Like, what does it mean that we're not able to predict individual level outcomes, in this case, migration, using the best data and the best predictive tools that we have available? First of all, the social survey data that we're collecting captures certain things about individuals, like their age, education, income, but we might be missing key aspects of people's lives. I also did field work a few times in Mexico, and some of the things that always come up are sudden things that happen, sudden crises that happen in people's lives, that somebody dies or their mother gets sick, and that becomes kind of a reason for migrating. So we're not capturing such things in the data. So that's kind of one explanation. Another explanation could be that our life outcomes or individual level decisions are kind of too idiosyncratic and they're subject to a predictability ceiling. So in computer science, maybe we're used to accuracy levels of 90%, 95% when it comes to things like, I don't know, what I'm going to buy next on Amazon or what movie I'm going to watch. But then with other kind of more serious decisions, maybe there's a ceiling to our predictive capacity. And in fact, I was kind of quite disappointed with 80% accuracy. And I was talking to my husband who applies machine learning in a different context using imaging data, brain imaging data. And he thought 80% was just fantastic, given that people might not know with 80% accuracy themselves whether they're going to become migrants or not. Now, these are kind of the downside of kind of our lack of being able to predict these things. But on the upside, we see that the simple parametric models that we typically use in the social sciences actually perform quite well, especially if the indicators that we put in them are based on deep domain knowledge. So this is kind of the positive takeaway from that. And that's what we're doing in the second half of the project. So we're asking, can we use our domain knowledge related to migration to specify and test very specific relationships rather than throwing everything at the model? And this part of the project is spearheaded by Julia Zhu. Now, where does our domain knowledge come from? Obviously, some of it comes from reading the literature, and some of it comes from doing field work in these vulnerable communities in Mexico. So in 2019, before the pandemic, we were able to go there with a team and talk to people about the effect of climate change on their, agricultural yields. So we spoke with coffee producers in Chiapas, and we also talked to corn growers in Jalisco. And some of the findings were quite kind of intuitive and things that, we would expect. And it was really striking that without us bringing this up, everybody acknowledged that things in terms of the weather were really different. And they established explicit links between, what's happening with weather, what's happening with their kind of production, and what's happening with migration. Now, many people mentioned that weather is a lot more unpredictable now. So the communities that we visited in Jalisco were right by Lake Chapala, a big lake in Mexico. And so the rainfall really determines how big the lake is going to get and how much land is going to be left for planting. And this farmer is talking about how they knew how much it would rain in a typical year. But then now it's really hard to predict. This farmer says, I invested money and the lake shifted, so you lose all the money that you've invested. Same thing with the coffee farmers. They're talking here about how they knew when the season would come, when would summer begin, when would spring be, but nowadays that's a lot more unpredictable. So then that really prevents them from optimizing the planting and the harvesting season. And then this was really interesting. This was not something that we talked about or thought about, and that really changed how we specify our model. So this farmer noticed that weather comes in different combinations. So not just it's raining less or it's hotter now, but when it rains, it gets hot. It used to not get hot. So we need to think about not just independent effects of these different weather conditions, but maybe we need to consider them in interaction. So how do things change when it's kind of dry and hot at the same time, or wet and dry, or wet and hot at the same time? And many people recognize that bad weather would reduce harvest, and poor harvest leads to debt because these farmers need to borrow money in order to buy fertilizers, in order to hire people to work their land. So basically, bad produce means not only that they don't have money, but they are actually in debt. So they need to take time for them to recover from that debt over the years. So this tells us that maybe it's not enough to just look at 1 year, but we need to consider multiple years to see how farmers are affected. And then migration is an alternative. Again, we didn't bring this up, but people did. So this farmer says there's no coffee produced anymore, and that's why young people are leaving. But migration in this setting is also costly. So nowadays, an average smuggler fee is around $3,000. So our data actually collects this information, how much people pay for smugglers. And it's increased over the years as the border enforcement has become stricter on the US side. It hasn't become necessarily a lot harder for people to cross, but a lot more expensive. Now, this means that if you have debt from a poor harvest, then it may take you a few years to be able to finance migration. So this tells us that poor and wealthy households might respond to weather in different ways. Okay, so we incorporated all of these insights into our modeling, and we kind of came up with a very specific model. So again, our outcome of interest is whether someone takes a first US trip, and we're linking it to precipitation and temperature in the previous time period, as well as 2 years ago. We're not introducing more lags because that would make our model really, really complex. And again, because we're not using machine learning, then overfitting becomes an issue. Now, we introduce the indicators that we previously considered, like age, education, household economic status. We also introduced state times year dummies. So these are binary vectors that capture changes in each state over time, or changes over time that are specific to each state. And this is important because agricultural productivity or agricultural yields have also been affected, not just by weather, but also trade in the Mexico-U.S. setting. And in some other work, we find that increasing trade with the US after NAFTA really affected the competitiveness of Mexican corn. So we don't want our results to be an artifact of that. So state times year effects help us absorb such changes over time. Now, this is our basic model, and then we layer several complications on top of this to test the specific ideas that our fieldwork suggested. First, we include interactions between precipitation and temperature to see how different combinations matter. Remember that farmer who said now it doesn't just rain, but it gets hot when it rains, so we want to capture that. We consider the full spectrum of weather. So a lot of the work in the literature looks at only kind of bad events like a drought or extremely high temperatures, but we want to capture the good years as well, when it's cooler than normal, when it rains more than normal, because those are the years in which you can save and later finance a migration trip if a bad event happens. We compare each community to its own normal to take into account potential adaptation. And we do that again by comparing each community to the weather in each community. We're kind of measuring it as deviation from its normal back in 1980 to 1990 period. And then finally, we introduce interactions between weather in T-1 and T-2. And this is to consider how sequences of events might create an impact, or whether kind of there's an intensification of responses. For example, this allows us to ask questions like, can a really good year make up for bad year 2 years ago? Or if you have 2 consecutive years of bad weather, does that suddenly create a response that you wouldn't normally see? And then we test for heterogeneity by household wealth status. So we estimate these models separately for poor and rich households. And in this setting, actually, all households are relatively poor. These are poor communities. But the way we distinguish them is if you own any assets like properties or land, you're considered wealthy. And this kind of roughly splits our sample into 2. Again, we use the Mexican Migration Project data, but we restrict our analysis in this case only to rural communities to isolate the agricultural mechanism. And this gives us information from about 56,000 individuals. Now, we focus again on the first migration trip between 1991 and 2018. We take the 1980 to 1990 period as the normal period, and then we compute the weather indicators as deviations from the mean in the normal period, divided by the standard deviation in the same period. So we have 5 weather categories for rainfall and for temperature. So very wet means you're outside 2 standard deviations of normal rainfall. Very dry means you're at the other tail. Same thing. So normal means you're within -1 to 1 standard deviations of normal. Okay, what do we find? That farmer was absolutely right. Combinations of rain and heat matter. So we find that it's not just about lack of rainfall, or it's not just about extreme temperature, but when things happen in combination, that's when we see an impact. And we also find that both good and bad weather matter. And we actually also find heterogeneity by household wealth status. So specifically, we find that wealthier households migrate when last year's weather is bad. So here we're showing some coefficient estimates, and we see that when it's very dry and hot last year, or dry and very hot last year, we see a positive migration response among the wealthy, but not among the poor. Poor households, on the other hand, migrate when last year's weather is good. So when it's wet and very cool, we see a positive response. So what does this mean? We actually can make more sense of these results when we look at sequences of weather events. And we see that poor households are actually migrating when there's a very specific sequence. The weather has to be bad 2 years ago, so dry and hot, followed by a good year, a wet and cool, where you save the money to finance a trip, and then you can send a migrant. This is not the case for rich households, and these households can immediately respond when the conditions are bad last year. So basically, there's a delayed response among poor households. So what are some of the main takeaways? Clearly, we see that migration is a possible adaptation strategy to weather in these communities, but then we see an inequality in this response. We see that wealthier households can respond to it a lot quicker than the poor. And from kind of an analytical perspective, we see that considering combination and sequencing of weather, and also their full spectrum, both good and bad cases, this is really crucial in understanding the weather and migration linkage. So connecting it back to kind of the beginning of the talk, I think they're kind of both useful. So the well-specified parametric model that we used in the second half, they're good because they offer insights into the mechanism. So we know that what weather events create what kind of an impact. But the non-parametric models that we saw earlier are also helpful because they offer information on the predictive capacity, overall predictive capacity, how well our models do on new data sets. So I'll stop here. I'm looking forward to more of a discussion, less of a monologue. Thank you for listening. I'll stop sharing now.
Thank you. Thank you very much for your talk. And there are a number of questions up on the Q&A, and I'm sure there'll be more coming in.
Absolutely. So, okay, so I'll start with Max's question. So Max asks, what implications does this have for public policy related to immigration? So, I mean, obviously, we see kind of climate change and immigration policy as two separate things. But here we're clearly seeing that there's a link between the two. And climate change, weather fluctuations, extreme events all have implications for immigration. So basically, we need to kind of think about whenever we're pulling out from the Paris Accord, this has implications for our immigration policy as well. So on the upside, we can also kind of turn this question and ask, like, is there anything that we can do about this in these communities? Is there anything that we would do that would increase the resilience of these communities? So we don't have very detailed data on that, but one piece of information that we have on these communities is irrigation systems and agricultural support institutions. So it's not clear what counts as an agricultural support institution, but in the data, there's information on each community whether such institutions exist. And we see that weather responses or weather-driven migration occurs much less frequently in communities where there's an irrigation system, so they have a buffer against weather changes, also in communities with these support institutions. So this basically tells us that there is some things that we can do to increase the adaptive capacity of these communities, but then we need to kind of think about and invest in these things. So I hope this answers the question. If not, feel free to add more questions related to that topic. Okay, so Maya. So Maya asks, will models have to be adjusted for increases in extreme weather events as a result of climate change? Yeah, so actually, Maya, so we were curious in the beginning that we thought we're kind of asking our data to do a lot, right? So we're asking when we introduce these interactions between temperature and precipitation. So for one, like, there's not many extreme weather events, we thought. Like, you have to be 2 standard deviations out to be considered very hot or, very dry. But then we quickly saw that there were many communities experiencing that, and the frequency of these kind of extreme observations increased over time. We were also worried that when we did these interactions, so we're asking now, not only kind of for you to be out 2 standard deviations in terms of the temperature, but also precipitation. And we thought, well, no community would be observed in that cell. And sadly, there are communities observed in those cells. And, remember, we're not even looking at 1960 to 1990 period. We're looking at 1980 to 1990 as the normal. So it's not even that far in the past. And yet these events are actually increasing over time. So yes, we're expecting these events to be more and more common, and it's already happening. And you saw already in 2000, there was no state that in the aggregate was in the blue shade, was receiving more rain than 20 years ago. All states were receiving either the same or less amount. So yeah. Okay, Sai is asking, I'm curious whether the random forest method was the first choice. Were there other similar methods considered initially? So yes, so this is a kind of a learning curve for us. We started with the random forest models because they are, first of all, their predictive ability is good relative to other methods, kind of reading from kind of computer science literature, but we didn't consider kind of more deep learning type methods. Maybe we should go there. We first wanted to start with these, and interestingly, random forests are probably the most applied method in the social sciences, and there's some work done by Stanford and MIT economists that are trying to work out how these methods can allow us to do causal inference. So basically, they've been more integrated into the social science statistical framework, I would say. So that was our kind of rationale for using them. But then I presented this to an audience that included computer scientists, and they immediately said, well, if you had used other methods, maybe your predictions would have been better. And they also said, maybe kind of your data are not large enough. Even with 140,000 observations, these data are actually not as large as, I don't know, kind of website clicks or kind of Netflix movie watching data. So they're still small compared to other data sources that computer scientists use. That being said, from a social science perspective, the data that we have from 140,000 individuals, that's actually quite large and quite rare to have such detailed information. So basically, if we're going to use these methods in the social sciences, we better get used to these data set sizes. And it's not going to be easy to kind of expand the available data. But yeah, that's kind of one of the directions that we're moving in. Okay, so Sarah asked a really good question. Are these data, the people in the ML model, completely independent from the others? And then do you consider people's behaviors affecting the decision of others? For example, the likelihood of a family to migrate together. So basically, there's many ways of splitting these data, right? So you can imagine we have 2 million person years, and you could say, well, I'm going to take like X number of communities and put them in my training data, and the remaining communities will be in the other portions of the data. But the problem with that is if the communities that you used in the training data are different from the other communities, then you might be training your model on a selected data set. So we basically, instead of doing that, we randomly selected individuals from each community. And so in the training data and in the validation data, we have different people. So it's not the same person. You don't have like 5 years of my life in one data set and 6 years of my life in the other data set. You have me in one data set, my husband in a different data set, potentially. And then the question about network effects is really prominent and really important in this setting, because in the Mexican setting, like one of the things that we've learned from years of research is that people first, migrate if they have family members, extended family members, community members who can help them migrate, because it's so risky and it's hard to know kind of where to go, what to do, that just wanting to migrate is not enough. And social ties are really, really important. And so in these models, we actually do include indicators of whether you have a previous migrant in your household and whether you live in a community where a lot of people have migrated. And that makes a huge difference. And in fact, if we separate our sample by the prevalence of migration in a community, we see the migration response to be higher in high migration prevalence communities. But that being said, we also see that at the community level, new migrants, or weather migrants, let's call them, are being drawn from families who haven't sent migrants before. So this is telling us that new families are joining the migrant stream as a result of this kind of environmental shifts. So it's expanding the base of migration in Mexico. Okay, so moving to Julie's question. Okay, so we started a few years ago with sub-Saharan African drought as factor in unwelcomed migration to Europe, and then migration from Europe to the Americas via Central and South America. Does your data include migration to Mexico? Okay, nice. So the data that we used comes only from Mexico. But the same kind of data collection effort was replicated in, I believe, 12 Latin American countries other than Mexico. And so we have that data as well. So it's called the Latin American Migration Project, not Mexican Migration Project. But the data there are much smaller. I think the country for which the most information is Dominican Republic. And I think in the Dominican Republic, there are only 9 communities that have been included. So compare that to 170 communities in Mexico. So the time frame, I think one advantage of using the Mexico data was because it was started early and because there are many, many communities there, you can basically project backwards and you can have more of a historical approach. I think with the Latin American data, it would be kind of harder to do that, but still we might be able to kind of detect some signal. And I think another way of reading your question is Mexico itself is also become a migrant receiving country in the last several years. And by some estimates, when we were visiting Mexico in 2019, some people were estimating there were at least 500,000 Central American migrants, waiting for kind of asylum applications to the United States at the time. So we visited the migrant shelters there and they were all kind of very full. And obviously that's an issue as well. And on the one hand, we can think of how kind of this environmental change is impacting migration from Central America. We can also think of kind of some sort of knock-on effects. How are Mexicans impacted by incoming Central American population? Is it creating more incentives for migration to the United States? And we don't know with the data at hand, but I think really important questions. Okay. I'll move to Ashni. Okay, so have you adopted your SML model to reflect the findings from your fieldwork? Yeah, so Ashni, this is actually how we came to think about these methods. So initially, I think we almost kind of adapted a very kind of computer science approach of like, let's throw all the data there and the models will pick it out. And increasingly, our thinking has evolved. And now we think the better data we feed these models, even the complex models, the more predictive accuracy we might expect. So now what we're working on is instead of using annual weather fluctuations, we're basically collecting data on what kind of crops each community is involved in. So if you're involved in corn production and also considering the region that you're in. So if you're in the Northwest region and if you're growing corn, what's your planting season? What's your harvesting season? And then looking at the weather conditions in that particular period, and then basically matching what community is doing to the weather and to the crop that the community is growing. And when we do that, when we kind of measure things more precisely, everything improves. So I think, again, kind of these average effects are interesting, but in the end, we really want to be able to capture the mechanism that we have in mind. And capturing that mechanism is also helpful if we're thinking about intervention. So if we can pinpoint that it's really the agricultural production, it's really the lack of rain in May that's leading to this, then we can maybe kind of inspire interventions that target that very specific thing. Otherwise, just being able to predict by itself would not be sufficient. So that's how we're thinking about it exactly. Okay. So David asks, I think, a methods-related question. So he writes, one of the main reasons for using OLS and inference is that it's cost-efficient, affordable to draw a probability sample from a population. If we start with low-cost access to big data, what advantages does machine learning offer relative to a similar OLS approach that would estimate parameters on some randomized sample of the data set, then test to see if those parameters are stable in other samples? Yeah, so yeah, David, I think one lesson to take away from the SML approach that I think I'll keep with me forever is the importance of this out-of-sample performance. So in the second set of the analyses, that when we're kind of proposing these very kind of simple kind of parametric models, we're still kind of leaving aside part of our sample just to see kind of how our R-square or the explained variation, share of explained variation shifts when we look at in-sample versus out-of-sample performance. So I think that's something that we as social scientists always need to do. Because, you know, I think sometimes kind of we get carried away by significance and say, oh, you know, whether it's significant. But then if you look at your R-square, you've explained less than, you know, 1% of the variation. So is it really a good model? I'm not sure. So I think it's helpful to know the overall performance of that model. So in terms of the other question, like if you have small data anyway, what's the use of, you know, SML? I think it's exactly kind of what I said in the beginning of the talk. When you have like complex interactions, when you don't have any social science theory or maybe field work to guide expectations of like what the lags to include are, what to interact with what, then I think it might be helpful to use these methods. And actually with Mario, after this kind of predictive paper was kind of disappointing, we used these models for a different purpose of, you know, feature selection. So basically, we wanted to see which weather measures perform the best in terms of predictive accuracy. And we gained some insight from that. We found that actually growing degree days, which are kind of the more precise measurement of weather beyond certain thresholds, within a specific period of like planting and harvesting, those measures performed consistently better than other kind of cruder measures. So that gave us the insight that maybe kind of we need to go further down this road of customizing the measures and capturing things specific to the community. So I think they're useful for purposes like that. You can gain insight from the data that you wouldn't otherwise be able to gain. But yeah, I think if I'm reading your message right, I think OLS methods also have much to offer there. Okay, Siobhan, what are some of the policy implications of for linking weather and migration? So I think showing the linkage in itself and hearing it in people's words, I think reaffirms that like some things are changing, and people who are farming are feeling these changes a lot sooner than maybe other people in the cities are not experiencing. So I think it's helpful to know that even before we started maybe talking about climate change at such a mass scale in the 1990s, people were already responding to weather by migrating. In the data, we can see that, right? So I think it's helpful to recognize that, and maybe kind of a share of the immigrant population in the US today are here because of the impact of weather changes over the years. And like an initial question in the beginning, these impacts are only going to grow with extreme weather becoming more common. So I think this is something that we need to really understand. And also, if there are ways that we can intervene that give people more options, like providing irrigation or providing insurance to crop losses, then I think that might also prevent some displacements that people would not otherwise be subject to. So I think it's really, really important to understand that. Okay, so I have no idea if I'm answering these questions well, but I'm hoping I am. So please kind of write your comments if there's more that you wanted me to talk about. So Manuel asks, did you look at how political, economical state of Mexico might be a compounding variable? Yeah, absolutely. So I think it's kind of hard to capture weather impacts because weather actually changes a lot of things, right? So weather might change the state's GDP, a community's economic organization. So there are many things. The fact that you can capture kind of the weather impact, even when you control for these other things, I think is quite remarkable. And I think we're adding a lot of, we're actually kind of running these models that are quite conservative in the sense that we're controlling for communities' agricultural involvement, we're controlling for state and year fixed effects. So if there are states that are impacted by, let's say, NAFTA, from 1994 to 1996, we see a big change. Those will be captured, taken away by the state times year dummy. So the changes that we're seeing here are within state changes. So we're really kind of holding our models to a high standard, and the fact that you can still see an impact is really remarkable. And actually the effects are quite large if we didn't control for these things. And once you control for these things, they still remain. So yes, the economic state of Mexico really matters. It's always there. The economic differences are there. But on top of that, having the distressor from weather really also creates an impact. Okay, so Joe is asking about individual health status. So there is some information in the data on this, but it's not changing over time. So the data set asks people about their health status now, and they also ask these questions, retrospective questions about like, how was your health before you migrated versus after you migrated? But those data are not very, very helpful. First of all, they're not available in all the communities. They only started doing this after, I think, community 70 or 80. So they're available in about half of the communities. And then I worry about recall, right? So when you're asking people about their migration 20 years ago, you know, how well might they recall their health before and after? But we could try to do that, especially if our main point is that maybe some of these unexpected events are leading people to migrate and we're not able to capture them with data. And actually, in the challenge that I talked about, the mass collaboration effort that I talked about, they tried to understand why their model's predictive performance was really bad. And they took these outlier cases, the cases where the predictions were especially bad. For example, the model predicted that you would have a 4.0 GPA, but you ended up having 2.8. So they found those people and interviewed them. And for many of them, actually, it was like a health event, losing a parent, something like that, that triggered, like that caused a shift in the trajectory. So I think it's really an important question to ask. Okay, so Brady is asking, is there a way to incorporate events happening within America that might deter migration to the US? So again, I think the state times year effects are subsuming that. But if we didn't include those, if we included, we have measures on things like border enforcement. We can also kind of model kind of policy changes at the state level in the US, state enforcement, and those all have, you know, an average impact. But even with those in, nothing can deter, or nothing will deter people who are desperate to migrate. I think that's kind of what we've learned through our analysis over time. You know, people find ways of migrating in this context, especially given the smuggling networks. If you can afford to pay a smuggler, then you can migrate. But I think that's an important point. Another question we can ask is, are there kind of things that the US is investing in, like environmental protections, especially on the border region in Mexico, that's actually helping? So I think that would also be a really interesting kind of unexpected thing to look at in the context of immigration. So how did Dr. Rodoval's background in bird migration contribute to this project? What can birds tell us about human migration? So actually, Amanda was so critical to this project because she always kind of asked the right questions. So initially, we weren't sure how to even kind of model migration, where to even get the data, how to think about it. So she was the one who inspired a lot of the measurement effort here, but she also suggested several kind of interesting directions we're yet to explore. So there's an index, for example, that's called the Human Footprint Index that measures the impact of humans on the natural environment. And so Amanda was the one to suggest that. And that's really helpful because that can help us understand how weather might be linked to migration in urban environments, right? So we know that if you live in a really built place, like full of concrete, then it's kind of overheated, or, so I think it's really helpful in that way. And one of the things that Amanda said also was that birds often change trajectory. So it's not that they're not migrating, but they take a different route to migrate. So that was an inspiration for another project where we looked at how weather changes or kind of extreme heat is related to what routes migrants take. Like, do they just shift course, avoid deserts? And we actually also kind of found some patterns there. So really generative to have someone like that on the team. Okay. Are we doing okay in time, in terms of time, Peter?
We have about 8 minutes or something.
8 minutes.
If
Okay,
that works.
so I think we have about 8 questions. So
okay.
Okay. So Zipporah asks, how does the location of communities affect migration, or were the results similar across all environments? Like, yeah, communities in mountains and dry forests. So we haven't modeled that yet at all. I think elevation would make a difference. I think a big aha moment for us was, I always assumed rain was a good thing, but then when we visited this community right next to a lake, for them, rain is good, but too much rain is not good, because then the lake basically expands and they don't have enough land. So I think, again, we need to kind of be more specific in how we consider the environment. We haven't done that yet, but I think that would be the next frontier. I don't know how to do that personally, but if we can find a geographer, someone who knows how to do this, I think it would be really helpful. So Ryan asks, yes, do you have plans to expand your research to more urban areas? How would you expect results from these areas to differ? Yeah, so I think urban areas are interesting. I think one of the ways that we can link this to migration in urban areas is a lot of people also migrate internally in Mexico in response to weather. And I think what we know from research is that some of these urban areas like Mexico City and some of these border cities have really expanded beyond capacity. So the infrastructure is not enough. They don't have water and they live in kind of shanty towns, people. And then that becomes a reason for migration, when basically cities become too kind of crowded and we see more migration out of urban areas. So that would be kind of an indirect link between weather and migration. In terms of kind of direct linkages, we haven't really figured out. But one pattern that we see consistently is that whereas in rural communities, lack of rainfall is really important. In urban communities, it's not about rainfall, but extreme heat seems to matter. We don't know why exactly people are escaping extreme heat, but that's something that we can detect with the analysis. So if that's helpful, yes, that would be really, really important, especially given that the most recent waves of migrants are increasingly coming from urban areas, not the rural regions. So Amy asks, how did you recruit participants, especially because you're asking questions about economic status and illegal border crossing? So Amy, I think it really helped that this study was being done in Mexico. And I think if you some of my students have done projects where they try to interview immigrants in the US. And obviously immigrants here are in a very vulnerable status. So you get a lot more rejections from them. And then as a researcher, you worry a lot about, their privacy and how you would protect that. I think in Mexico, again, we worry about these kind of protecting the data by itself, but I think people are more forthcoming because we also collaborated with a team at the University of Guadalajara. So a regional institution is involved and the team recruits its members from local students there. So I think this all increases the trust that people have that their data will not be used for other purposes. And I think the MMP had an acceptance rate of about 95% until kind of very recent years. After 2006, there was a war on crime in Mexico. So that's when homicide rates really went up. There was turf fights between cartels. And then also these kind of organized crime became involved in kidnappings. So they would kind of call you and say, we have so-and-so in the US, if you don't send us X amount of money, he's going to be killed. So people became wary. In my first field work in 2011, some people refused to talk to us because they were worried that we would use their information to extort money from them. So that's definitely a concern. But for most of the MMP data project, this hasn't been an issue. Yeah, Ashni asked a similar question. Any resistance to discussions about migration, sensitive subject? I think once people agree to talk about this, they've been really, really open about kind of providing this information. And remember, we only ask about, their first migration trips. For most of them, like it happened in the past. It's not kind of recent migration. So we've been lucky. But I think the US data collection effort is actually a lot harder. Okay, so Connor asks, did you consider using 1980 as your normal instead of using the 10-year period and compare? Yep. Yeah, so we've tested our results against using a different normal between 1960 and 1990. The results are not that different. I think the more kind of you bring the normal to today, the less data you have to analyze. Remember, you can only analyze after the normal period. So if we were to use 1980 to 2000, then we would only have data from 2000 to today. So I think that would be helpful in understanding what's happening now, to be able to kind of predict things more accurately now. I think for this kind of initial cut, we wanted to have kind of a historical lens. So I have 2 minutes. I'll very quickly read Julie's questions. Yeah. Okay, Julie wrote a very nice comment about thank you to Latin American project too. Okay, I appreciate the comments, Julie. And David asks, is there a comparable data on relationship between weather and income? Yes, definitely. There's data on internal migration and there's linkages, but I think in this setting, international migration is a more kind of consistent response to weather changes. I think the internal migration results are more kind of all over the place. Okay. Thank you so much. I'm sorry if I did not answer your question. I think I tried to go all of them.
That was great. Get through a lot. It was lots of questions. Very good. Very interesting talk. Thanks so much for coming in and talking to us.
No, my pleasure. Thank you so much for the questions. They were really, really helpful.
Okay. All right. Bye-bye. Thanks
Bye.
again. Bye-bye.